All right, everyone, let's get started. So today we will be discussing probe tasks and trying to figure out what the representations of these language models that we have been talking about for this entire semester, what are these representations learning? So if you go to ChatGPT, right, you can ask it a bunch of questions and you can ask it, for example, what is the capital of Massachusetts, right? And it should output Boston, and you might, infer from this interaction that it knows that the capital of Massachusetts is Boston. However, we know that there's, we only have black box access to these models, and the model may know, or to some degree, various facts that you can't really access by simply prompting it. Like, you might not know what the right way to construct your prompt is to elicit that knowledge from the model. If the knowledge that you want to probe is not simply like an entity or a single word, but rather might require some sort of explanation, then you run into the issue where your decoding algorithm is a confounding variable, right? You might get different inputs based on different hyperparameters or different samples that you take. And so this is really like a two-part class. Today, we will be focusing on what can you learn if you have access to the model's internal representation. So the hidden states at every time step, the final layer hidden states. Can we do some stuff on top of those vector representations to understand what the model has and has not learned? So on Monday, we will be talking about in-context learning. So this is the case where you just have access to the model via prompting it. We will be talking about how that works and some preliminary hypotheses that people have developed in the field to understand how, by just giving the model examples of a task or instructions in the context with no further training at all, the model can start to solve some tasks that it's never seen before. But this lecture forms some background that of what people have studied in the past with models like BERT and T5 and Roberta, where it's actually feasible for you to extract the weights and examine them. So this general kind of work has been branded as Bertology. There's a nice survey paper that studies all of the different types of probing that you can do on top of models such as BERT. And really, like, you can go very, very far into the weeds here. You can look at, for example, what does the attention head at layer 16, the fourth attention head, what is it learning, right? What properties is it sensitive to? What is it not sensitive to? You could look at, the hidden states at layer 4 versus layer 24 and see if there's, any differences in what kind of information those hidden states are encoding. So to summarize, in this lecture, we will focus on the case where you can access all of the model's internal representations. So there's many tools that you can use right now if you're working with some of these smaller models to understand what kinds of knowledge is present in their representations. So Hugging Face has this Bertology module where you can explore like different hidden states, attention weights, and get all the attention head outputs and the gradients, so you can do this kind of fine-grained analysis. But it's an interesting question, like, what should you do with all of that information, right? Because imagine you have a model that has hundreds of layers and 100 attention heads at each layer, something like GPT-3 or GPT-4. How do you make sense of all of this information, and how do you find patterns in these internal representations that actually mean something? So there have been some results of kind of improving these models that have arisen from just inspecting these attention distributions and the hidden state. So for example, this paper in 2019, are 16 heads really better than one? This work found that the attention maps of many of the heads in each layer of a BERT model are redundant. Like they look at the same, they assign high probability to the same tokens in the input sequence. And so at test time, if you just remove some of them, you don't really lose that much performance on a couple different tasks, including machine translation. So this could be a good way to post hoc look at your trained model and prune it to make it smaller so that when you deploy it, it is cheaper. There's been a lot of work on exploring what kinds of linguistic properties these models learn, right? Can they learn things like low-level things like part of speech? Can they learn more higher-order syntactic dependencies or discourse-level dependencies between sentences? Can they learn properties like co-reference, other things like that? So we'll talk more about this line of work in this lecture. So first, I wanted to show in a demo from this Allen NLP interpret library that allows you to kind of explore the masked language model objective in BERT. So how does this work? I guess I can click this. Okay, so and this is fairly similar to your homework 2. You're just exploring the masked language model objective of a pre-trained BERT model. So I can give it, for example, this input sentence: the doctor ran to the emergency room to see mask patient. And you want to, get a distribution over the words that could fill in this mask token. So if I run the model, you can see that first of all, this sentence is a good representation of the gender bias that is encoded in these models. You can see that his has a probability of 38%, the patient is 37%, her patient is only 6%. But this you can just observe by looking at the probability distributions. You might want to know why this word his has a high probability and why her does not, right? And so you might want to ask the question, when the model is making this prediction of what is going into this mask token, which words in this sentence are contributing the most to this prediction? So that's one example of a question that you might ask with a probe. So one way to look at this is to visualize the gradient. So you can actually look at the norm of the gradient of at each of these word embeddings to see which one is contributing the most to this particular prediction. So if we do that, we see that the top 3 most important words, as computed via just looking at the size of the gradient, are doctor, C, and patient, which makes sense. So the model has likely learned through its objective and through the data sources that it's been trained on that doctor and his or he they co-occur more frequently than doctor and she, and so it is just spitting out this representation of the bias in its own training data. So we'll talk later in the semester, probably in a couple of weeks, about how these kinds of models are not just reflecting the bias that is present in their training set, but they're actually amplifying the bias that is present. So let's say doctor and his co-occur together maybe 70% of the time, and doctor and her co-occur 30% of the time. If you train a model on it, you observe this amplification phenomenon where the model might predict his in 90 or 95% of the cases, which is even more than the bias that's present in the training distribution. So we'll take a look at that later on in the semester. Yeah. So it is kind of like a proxy, but you can compute the, like, you know, if you are predicting the next word here, you can compute the gradient of the cross entropy loss with respect to each of the individual word tokens and figure out for this prediction of, say, the word his, which of these words was. But again, it's not a perfect, like the correlation between the norm of the gradient and the actual importance is not guaranteed to be true, but that's why they offer many different types of visualizations. So I'm not actually sure what this one does, but okay, it's totally different. So it's hard to draw conclusions from these kinds of things, and there are far more intricate methods that have been proposed to like trace back through the attention maps exactly all the way from the top layer prediction to the very bottom to see, you know, what word is actually being attended over the most, but it's a very hard problem in general. Okay, so anyway, this was one example of a visualization-based understanding of the model, right? You are trying to figure out what are the most important words to making this prediction in a particular context, and in doing so, you might achieve some degree of understanding over the model's behavior in that context. So, yeah. Sorry, that what is not the high? In this example, the blank rushed the emergency room to see her patient. Oh, a patient. So here the mask, this is a different example. The mask token is on the subject of the sentence. Oh, in the previous example. Yeah, let's see. You mean over here? Yeah. Uh-huh. Yeah. Yeah. It could. I mean, we could try a different sentence here if there's some modification we can make. That's oh, okay. Yeah, we could try nurse. Maybe the article probability of article will be higher here. No, it's it's the same. Yeah, I mean, again, it's very hard to explain this behavior because this model was trained on Wikipedia and like some unpublished books data, and you have no idea what the composition of the data set is. So it makes a big difference. Yeah. All right. What am I doing? Let me go back here. Okay, so when we're trying to understand the behavior of these models, we can either do visualization, like in that demo, or we can devise linguistic probe tasks, which actually allow you to train a small model over the representations of the large pre-trained model to check whether or not the representation contains any information about a specific type of knowledge that you want to probe for. So we'll start with the, we'll continue with the visualization theme. So this was one of the most, I guess, famous results of visualizing the neurons of a language model. So this work was actually published by OpenAI in 2017. They trained a recurrent neural language model, and they just trained it on next word prediction. And then they wanted to use the hidden states of that model as representations to do sentiment analysis. So what they did was they trained a small classifier over the hidden states of their language model. So if they get you know, a review like this movie was awesome, they might take the final hidden state after encoding that full sentence, and they would put a classifier over it. And then they were trying different types of this classifier, and one thing that they did was put an L1 regularization penalty over the classifier. So this encourages the model to, the classifier to use as few features as possible. And they found that its performance was really quite consistent, even though it was using surprisingly few of the learned units, which is a quote from their article. So once they looked further at the neurons, so the actual dimensions of the hidden state that were contributing to the sentiment prediction, they found one neuron in particular, which they called the sentiment neuron, that seemed to be very sensitive or correlated with the sentiment of the sentence. So you can see here the distribution over the values of this single dimension of that hidden state for positive reviews on the right here. So you can see that it's quite sharply peaked at a value at about 1/2. And negative reviews where it's the value of this neuron is also negative. And this behavior arose from just next word prediction. So the model at some point realized that maybe encoding the sentiment into its representations was helpful for predicting the next word. And this single neuron somehow became responsible for, or it contained that information. And so there was nothing in their training procedure that said that this neuron should be responsible for sentiment or that there should just be one neuron. It's some sort of function of the training process and the data that they trained this model on that they were able to see this behavior. But it's probably one of the few success stories of actually looking at the specific values of these neurons. In general, if you have 100 layers or something, this is extremely hard to do, right? What if there's one neuron at layer 1 and 10 neurons at layer 5 that all encode the sentiment to some degree? Like, it's very difficult to tease out these patterns. But this shows that it is possible for very simple and small and shallow networks. How did they know that the model used few of the learned units? They could control how few of the units the model was learning by modifying their regularization weight. So if they apply a very high regularization penalty, the classifier at least is forced to use fewer of the neurons during its prediction of the sentiment. So this is a picture of a visualization tool called LSTM-Viz, which was developed in 2017 to try and analyze the actual values of the weights of these neurons and the actual weights of the weight matrices that are used to make these predictions. So you can see there's a ton of heat maps, there's this line graph at the top, and it is overall incredibly difficult to make sense of things like this. And this is just for a small recurrent neural language model. If you imagine doing this for a transformer with many, many layers, this is not at all useful, right? Like, you can't just look at this and see that there are patterns, or if you were able to, it might take months of just inspecting these things and writing some scripts and so on, and so it might not be the most efficient way to figure out if some property that you care about actually exists in the inputs here. So that kind of motivates this other line of work on understanding these models, which is called linguistic probing. So here you are actually training a separate model, so it's kind of similar to what OpenAI did. But your goal is not to identify one neuron or 2 or 3 neurons that correlate with a particular property. Your goal here is just to identify whether or not a model has learned some particular property of the input language to some reasonable degree. So you're not caring about localizing that knowledge to a particular part of the hidden state or the model weights. So let's see how this works. These are from some of the first probing papers that were released basically concurrently with BERT. So let's say we get a representation of a sentence from a large pre-trained language model. So well, we can think about BERT, right? It's easy to get a representation like this from BERT. We can just extract the CLS token final layer representation, and we have a single vector that we can say contains the model's encoding of that sentence. So now we're going to put a classifier over this vector representation of the sentence. So how do we implement classifiers? Like, how have we done this in the past? Let's say I wanted to have a sentiment classifier over this, this sentence representation. What would I do? Right, so I would put a fully connected layer or linear layer or whatever you want to call it over this representation. My goal would be to project it down into the space of the possible labels that I have. So in the case of sentiment, I would have 2 labels. In the case of some other type of probe, I might have a different number of labels. Then I would apply a softmax layer, right, and actually train this model to predict whether or not whatever property I care about is present in the representation. So let's take a look at a very simple one. We might want to know, for example, if BERT understands how long a sentence is. And by how long, I mean how many words are in that sentence, or how many tokens. So if my goal is to predict the length of the input sentence S, I could formulate this as a classification problem where I might have different bins of lengths. So like all sentences that are fewer than 5 tokens, sentences from 5 to 10 tokens, sentences from 10 to 15, and so on. I could also formulate this as a regression problem where you're trying to predict from this representation exactly the number of tokens that is present in the input. Regardless, I would use the same setup with this fully connected layer and then either a cross entropy loss for classification or something like a square loss for regression. Wow, that was not good animation there. So an important property of the probe network, which kind of differs from what we saw in BERT when we were applying it to downstream tasks, is that it is critical to keep this sentence representation frozen, which means we do not apply backpropagation into the underlying BERT model. So why is this? Let's say our goal is to understand whether or not BERT encodes sentence length. Why might we not want to backprop into the actual BERT model that's responsible for creating this representation? Exactly, right? So we want to know if the pre-trained model understands sentence length. If we are adjusting the model, if we're optimizing it to predict the sentence length, then we are defeating our own purpose, right? We want to explore the pre-trained model. If we change that model, we're no longer accomplishing our goal. So this part is very critical. It is important in any kind of probe task. You need to keep the method for obtaining the representation frozen throughout. So every time I see a particular sentence, it's going to have the same representation. The only weights that are changing are those of this classifier that you're training. So this classifier is implemented by a feed-forward neural network, same thing as fully connected or linear layer that is trained from scratch. So it's randomly initialized, and you train this by giving it examples of BERT representations and the corresponding length of the input sentence. You might have some small training data set for doing this. You train this classifier, and then you observe its performance on a test set of new sentences that the classifier has not seen before. So the idea is that if the classifier learns this property, if the property is easy to pick up from this representation, then it will be able to generalize to new sentences in the held out data. On the other hand, if the classifier is not able to learn this property from the representation and the labeled data that you provided, it might be able to overfit the training data, but it's never going to be able to generalize to new sentences. So the size of this probe network and the complexity of the probe network is a very important factor in these analyses, as we'll see a little bit later on. All right, so any questions about this overall format?
So the representation that we're feeding in is input to the classifier, taken from some intermediate state of the word model. Is that correct?
Yeah, so in general, if you're doing like sentence level or sequence level probing, you're going to be taking those representations from the final layer of the pre-trained language model. But as we'll see, there are also some interesting papers that do these probe tasks over every different layer so that you can see, for example, maybe the sentence length is not encoded well at the first layer of BERT, but it is at the 24th layer where it's had much more opportunity to, take information from across the entire sentence.
So would you be able to ask questions like, does layer 24 include my verb test, and then take tokens from 24 and feed through this?
Yes.
Okay.
So you could compare, for example, does layer 24 encode verb tense information with a higher degree of certainty than, say, layer 14. Maybe layer 14, that information is not really present in those representations. Yeah. So you can consider a neuron is one of these blue circles here. So it's just one of the values in the representation. A layer is, yeah, I mean, these terms are a little vague. So when we've been talking about layer, we've been talking about like computations that are then stacked on top of each other. So right in a transformer, we have these quite complex series of calculations with the attention, the feed-forward layer, and residual connections, which we all combine into one layer or block. When we talk about the 14th layer versus the 24th layer, we are referring here to the representations, the vector representations, the token level vectors that are the output of that 14th layer, the calculations that go into that. So a neuron is then just one dimension of one of those representations. Is that clear? So a neuron is a single number. It's a scalar, and a representation is a vector, so it contains many of those neurons, and you have many of the representations at each layer and for each token. Other questions? This is a great question, and we'll get to this later. So, of course, if, let's say, I train this model, and then on my test set, it gets like a 60% accuracy, I could say maybe the model has some idea of sentence length, but not a perfect idea. But it's not clear if that's because the information is not contained in the representation or because my classifier was too weak, right? What happens if I add 2 layers to my classifier instead of 1? Maybe I'd be able to get 70% accuracy. What if I have 50 layers in my probe network and I get 99% accuracy, right? What does that tell me about the information being encoded in the representation? So as we'll talk about in a bit, you do need to control for the complexity of the probe network, and you can do so by using what are called control tasks, which we'll see in a couple slides. Yeah. Mm-hmm. So you might have a classifier that predicts the tense of the main verb in the sentence, and you have to produce those labels yourself. So maybe you manually annotate like whether this is in the past tense or the present tense, or future tense, or maybe you acquire that automatically from some sort of parser. But regardless, the data set that you train your probe network on, it has to contain labels either from manual annotation or from some process that can give you those labels. But generally, these probe objectives are very simple. So, like part of speech is a straightforward thing to probe for. There's many data sets where people have gone and labeled the part of speech of different words, so you can use those in your probe classifiers. Oh, you mean the question in, so does the 14th layer of BERT encode information about the tense of the verb? So if I were to make that more specific, I could say something like, do the representations, the token level representations at the 14th layer of BERT, do those have information about the tense of the sentence? So I could imagine putting a classifier over the CLS token that you get at the 14th layer to predict past tense, present tense, or future tense. I could even put it over the verb of the like the representation associated with the verb. Yeah.
So earlier you were saying the definition of a neuron can change based on the context. And you were explaining the 2 questions ago.
So a neuron is always a scalar. It's any number that is part of any representation, either the final layer or the intermediate layers of the network. Yeah, sorry, that's right. The word layer is more vague. I think maybe that's what I was referring to when the definition can change based on the context.
Okay.
Yeah. Okay, I see some YouTube question. The size of the probe network should not matter, right? That is not true, as we'll see in a bit in response to your question as well. How did they make sure the probe network learned the count? So you can measure the training accuracy, like does this classifier predict correctly the length of a sentence in the training data? You can also measure the test accuracy. So for sentences that are not in its training data, can this classifier correctly predict the length? And so in general, like if the model gets a high test accuracy, that's a sign that the model is actually learning to predict the length of the sentence from the representation and not just overfitting to the training data. It's very easy to make the classifier reach 100% accuracy on the training data, but it's only possible for the model to generalize to the test data if this information is present in this representation. Okay. Wow. Okay, so here's another probe task of word content. So here, you actually have 2 inputs to your probe network. The first is the word W, a candidate word, and you're asking this question, does this word appear in the input sentence? So I might have a sentence like, John went to the store, and I might have a candidate word like bug, and I feed both the CLS representation of the sentence, John went to the store, and I feed a word representation of the word bug, and I train my classifier to predict yes or no, does this word occur in this sentence? So here you're actually probing the content of the sentence representation. You want to know if BERT has encoded information about all of the words in the sentence into this final layer CLS token. Yeah. Yeah, it's a good question. So where does the word representation come from? So you can get this word representation in many ways. Again, it's not trained during this process. So you could use, for example, BERT's own word embeddings, or you could use external word embeddings from things we haven't talked about, like Word2Vec or so on. It's just some representation of the word. So in general, you would want to use the pre-trained word representations from BERT. But it becomes a little tricky if you want to probe for phrases. Then you might want to use some higher level representation, like maybe a CLS representation of just encoding that phrase. But this task is a little tricky because you now have this added dependency on a word representation. That word representation might itself not be very powerful. And so if it doesn't indicate like what kind of word this is or what the meaning of the word is, it'll be hard for the classifier to make this distinction. But this is another task that people have tried. And you use the same exact format as before. You train this classifier. You can imagine it's very easy to create data for this task, right? I can just take an arbitrary sentence, either sample a word from that sentence or sample a random word and then ask, like, is this word in the sentence or not? Oh, God. Okay, and hopefully this is the last one on this poorly animated slide. You can also predict, see if, yeah. Yeah, so it's a fairly difficult mapping task, which might require you to have a stronger classifier here. But in general, that is one source of complexity in this kind of task, which requires two inputs. And we see here a task that requires 3 inputs. So here, you're given a sentence, and you're also given 2 words that occur in that sentence. And you ask, can the sentence representation, just from the sentence representation, can you predict whether word 1 occurs before word 2 or not? So here, this is just a binary classification task. You have these 3 inputs. You have the sentence representation, word 1, word 2. Does word 1 come before word 2 or not? And again, these word representations could be from BERT's subword embeddings. They could be from some external embeddings as well. The end goal is to see if the model has captured any order-based information. So you might think, obviously, the model has captured order-based information, right? Because it has position embeddings at the input. But remember here, you're probing the sentence-level representation. So you just have one vector that is supposed to be used as a representation of the full sentence. If this vector does not encode whether word 1 came before word 2, that's probably pretty bad. So yeah, this is another property that is commonly probed. So you mean, can we combine like all of these tasks into one big probe model? So in general, you want your classification task to be as simple as possible. So if you imagine you combine all of these together, or maybe you could combine like, I don't know, this one and this one together, it would be kind of awkward because like what is the classifier actually predicting? Would it be both the length and whether this word occurs in the sentence or not? Like you would have to multiply your label space in order to handle all the possibilities. So in general, people use separate classifiers for each of these simple questions. Yeah.
What would you do with the results of this classifier? Are you going to get feedback on how to improve your main?
Yeah, that's a great point. So okay, let's say I train these 3 probe networks and I get some numbers. So maybe it has like 90% on sentence length and 80% on this word content and 70% on this. What does that even mean, right? So in general, it's useful to know where the model is struggling. And if you have a downstream task where it's critical for the representation to, say, contain word order or something like that, you can actually fine-tune the model on the probe objective itself to fix this, right? If you know that the model is not very good at word order, then I can just redo this process, but allow the backprop to flow through the BERT model. And that would ideally increase the performance on the probe task. However, this is not like a perfect solution, because as soon as you fine-tune your pre-trained model, you risk losing or adjusting some of the pre-trained knowledge itself, which might have been useful for the task. So yeah, it's a good way to evaluate various pre-trained models in general, and you could use it to correct some information or add some information into the representations that it might be losing before. We'll talk about that a little towards the end of the lecture, but in general, it's mostly used to evaluate different pre-trained models against each other.
Would it be helpful if we post-training on those sentences first and then we will train the classifier?
So you mean fine-tune the BERT model first?
No, it's further pre-training on the sentences that may be involved.
Oh, yeah. Perhaps, yeah, but generally the sentences that are chosen here are very, very simple. They might even be from the training data of the model itself. So yeah, it's a good point. Maybe the model, if these sentences are very strange or out of distribution for the pre-training data, it may need to be pre-trained more on the probe data. But usually the probe data is small, first of all. It might be a couple thousand examples. And the sentences are relatively straightforward, simple. They don't have some strange vocabulary. So I don't think you would get much benefit of that. Yeah.
So, let's suppose the sentence length is very for a downstream task and not very long.
Mm-hmm.
So instead of fine-tuning based on the fine-tuning part of the sentence length, we can also fine-tune it on the entire downstream task. Because fine-tuning on sentence length might throw off the balance with some other objectives which are important for our downstream.
It's true. You may, if you have enough downstream task data, then obviously it's much better to just optimize for your downstream task. But you could imagine some situation where you have a collection of downstream tasks, or that sentence length is very important in general for your use cases. And you want to have a pre-trained model that you can easily adapt to all of these cases. Perhaps mixing in some batches of sentence length prediction is not a bad idea. So people have tried many different configurations of these kinds of probe objectives with downstream task objectives, like mixing batches between the two. In general, of course, all of this is now obsolete due to ChatGPT, but yeah, it is a thing that has been heavily studied. Okay, so here's a more interesting probe task that is focused on whether or not these models have learned the concept of co-reference. So in this phenomenon, you're basically looking at whether or not two mentions or spans in the sentence are referring to the same entity or event. So I could say, for example, actually in our demo example here, the nurse ran to the emergency room to see her patient. Here, this nurse and her would be marked as co-referent. They're referring to the same entity. So you might want to know whether or not this BERT model can understand that these two mentions are referring to the same thing. However, this is not very straightforward to do in the methodology that we just discussed on the previous slide, right? Because now we're actually talking about whether two specific words in the sentence are referring to each other or not. And so here we might actually do our probe over the token level representations for, say, nurse and her. We might take those two representations and concatenate them together, feed them into a classifier to say, are these co-referent or are they not co-referent? So here's a case where you're not just using the CLS token. In fact, you're not using it at all, right? This would be the CLS token. Instead, you're using two different final layer token level representations as input to your probe task. Does that make sense? Yeah. Mm-hmm. Yeah. So in that case, so I guess your candidate sentence was John's mom went to see either his or her sister, and that his or her would depend on, like if it was his, it would refer to John. If it was her, it would refer to the sister. So in that case, you could have two candidates, right? You could have actually you could have John and his, Mary and his. Yeah, so you'd have two candidates, and you would see which one has higher probability of being co-referent. In general, the training data for these kinds of probes comes from annotated data sets of co-reference. So there are some very hairy cases where there's many different entities present and many pronouns, and resolving those requires a lot of context. And those are the ones that are of most interest, right? Because you want to know if the model has a good understanding of the sentence, which requires it to understand the co-reference. But you can boil all of that down to binary decisions between pairs of entities in the sentence. Actually, co-reference resolution as a task is generally solved as a pairwise classification decision. So first you detect all the mentions in the sentence, then you classify whether each one is co-referent or not. And in doing so, you can form a bunch of clusters of things that are co-referent and things that are, or different clusters of entities. Okay, isn't it hard to predict this based on the representation of only 2 words? Should we also include the sentence representation in this case? Yeah, you could include the sentence representation, but you should remember that these token representations are contextualized, so they do include information about the entire sentence, not just the single word. So it's not required that you need to also provide the CLS representation, right? These final layer token level representations are themselves a product of unmasked self-attention for many different layers. So they have information about the entire sentence. All right. So let's just summarize some of the motivations of these probe tasks that we've discussed to this point. So the first point is that if we can train a classifier to predict some property of the sentence, and we've looked at a couple different properties now, based on just these vector level representations, it means that that property is encoded somewhere in the representation, right? That's the main takeaway from this set of experiments. And if we cannot train a classifier to predict that information, that does not necessarily mean that the representation is not, the property is not included in the representation. It might mean that it's just very difficult to train the probe network to elicit that information from the representation. So that's what this means. Not encoded in a useful way means that that information might be buried somewhere deep down in the representation, but it's not immediately obvious on the surface. Like the most obvious example would be that sentiment neuron, right? Like any probe network would just latch on to that one neuron to predict the sentiment, but maybe something like coreference is not so easy to determine on just the values of a particular neuron. Perhaps in general, if you can't get this property out of the representation with a simple probe network, then it's not likely that a downstream classifier for a different task can make use of that information. So that's the general motivation. Okay, so let's look in general at some of the characteristics of different probe networks. So usually the tasks are simple classification problems, usually centered around very simple linguistic properties. And in response to your question, it's important to ask simple questions to minimize issues with interpretability. So if you ask like some complex multi-stage question with a large output space, it becomes harder for the classifier to actually perform this task. In response to someone's question, I think the one in YouTube, The methodology is agnostic to the architecture of the probe network. So you could have an arbitrarily large probe network, but this is the talking about the encoder. So I could use this for Bert, I could use this for Roberta, I could use this for any model that gives you a vector representation of a sequence. However, the probe network itself, it could be any architecture. Like I could make my probe network a transformer, or I could fine-tune a BERT as my probe network, but you do pay a price because as your probe network gets more complicated, it's not clear if the information that you're searching for is easily accessible in the representation, or if your probe network is just able to find any sort of pattern in the data set, as we'll see. So overall, the process is you have some encoder network, or even you could use this for a decoder only model, right? I could take GPT and take if I have a sentence like John's sister visited her sister, oh my God, John's mom visited her sister, I could pass that sentence through GPT-3. I could look at the token embedding at every word, and I could take the embedding for the final word of that sequence, which has information about all of the words in the sentence. I would freeze the model, regardless of what the pre-trained model is, and I will only train a tiny classifier on top to predict whatever property I care about. Okay, so let's take a look at some other kinds of tasks, and we'll look at these a little more detail in the rest of the lecture. But for example, one cool thing I could do is probe for numeracy. So whether or not this model, like BERT, can understand that, say, 9 is larger than 7, or that, you know, if I have a bunch of different numbers, 9, 4, 12, 1, 11, that 12 is the maximum of these numbers, right? I could also look for things like, can BERT do addition? I could give it 2 word representations of numbers, like 7 and 2. This is literally my input, and I would encode these with some BERT or whatever. I would pass them into my classification network or regression network here, and it would be trained to predict the sum of those 2 numbers. So if this output of the network is close to the actual sum of the 2 numbers, I could determine that the model has kind of learned to do addition. Obviously, this has a lot of caveats, right? Like, if it can only do addition for 1-digit numbers, that might mean it just memorized those sums, right? Ideally, it would be able to do addition for you know, any sort of 3, 4, 5, 7-digit numbers. If you look at the papers that probe numeracy, you'll see that most of these models are really bad at this task. Most of these models referring to BERT-like models. However, if you look at ChatGPT or GPT-4, they're actually very good. And one reason for this is, well, there's probably many reasons, but one is that those models are also trained on code. And training on code, it is hypothesized that it really you know, induces several more reasoning-ish behaviors of the model rather than just training on text alone. And also, we don't know if those models have been instruction tuned or tuned with human feedback to learn these like simple mathematical functions. And not to get even more on a tangent, but we talked about methods that actually integrate external APIs into these language models so that, you know, it's probably unreasonable for us to expect a model to learn math by just next word prediction. But what if it had access to a calculator, like in the tool former? Then it can actually learn how to use a calculator as opposed to learning how to do the math itself, which might make it far more efficient to use for various problems. Anyway, so back to your question, we were talking about like probing at different layers. And in general, the takeaways from a vast body of work on linguistic probing is that the lower layers, so the ones closest to the word embeddings, focus more on like local syntax, which makes sense, right? They have not yet had the opportunity to have a lot of different contextualization over the entire input. The upper layers, on the other hand, so those focus more on the semantics of the sentence, which is, when you're predicting the next word, both the syntax and the semantics is very useful, right? You might want to know, for instance, that you're predicting a noun next, but you also might want to know what kind of noun. And so both of those have to be present in the input. So here are some plots. This second row here has a 6-layer transformer BERT-like encoder-only model. And this is the performance on part of speech tagging. So can you tell whether a particular word is a noun or verb or adjective just from the token level representation at that layer? So if you look at just the first layer, you're getting pretty decent part of speech performance, but this performance degrades as you get higher and higher up the network. And yeah, not as conclusive for parsing. It looks like for parsing, which we haven't talked about at all in this semester, sadly, one of the middle layers here is actually the best for this task. For coreference, which we just talked about, is figuring out whether two mentions are referring to the same entity. It looks like the higher level layers or the middle layers are best for that, and the lower layers are not great. So you can make these kinds of high level conclusions. This paper, Tenney et al., finds out that a model like BERT basically reproduces all of the steps of what used to be the traditional NLP pipeline, of which we've talked about almost none of these tasks because they are not really performed anymore for solving any downstream problems. But it used to be the case that if you wanted to use NLP, you would have to do part of speech tagging, you might have to do parsing, detect all the entities in the sentence, do coreference, and then you would have enough features to put them into a classifier to solve whatever task it is you care about. And it turns out that BERT, just through its pre-training objective, is fairly good at all of these low-level tasks, despite not ever being trained to solve any of them. So you can see here, this is showing the optimal layer representation for solving a particular task. So they do this by basically training these probe networks over over the representations at different layers. So here they're plotting the expected layer at which the probing model correctly labels an example. So for these low-level tasks like part of speech tagging, constituency parsing, and dependency parsing, the expected layer is pretty low down in the network. But for tasks like coreference resolution, semantic role labeling, and relation extraction, you can see that these more semantic-oriented tasks are best solved with representations from higher up layers. So this is pretty cool. You can kind of correlate what the model is learning to the performance on these well-studied NLP tasks that are focusing on a specific type of linguistic property. All right, any questions about this? Okay, so right, I realize now that since we haven't talked about parsing, this might be a little confusing to some of you. But one important question that in particular linguists are very interested in are, do these language models encode syntactic structure? So that this tree-like structure of a sentence. We talked briefly about, like what is a noun phrase and what is a verb phrase. The chef who ran to the store was out of food. So here, if you're doing language modeling and you're predicting, say, the next sentence, you would probably need to know what was out of food, right? Was it the chef who was out of food, or was it the store? Like, what is this was out of food modifying? And if you have a parse of this sentence, you can see that was here is connected to chef, because the chef is the one who's out of food, right? But if you interpreted this sentence wrongly, you might think that was is modifying store. And so these different structures lead to very different interpretations of the meaning of the sentence. So if the chef who ran to the store was out of food, and if was connected to chef, then you might have this second interpretation here. After stocking up on ingredients, the chef returned to the restaurant. So the chef was out of food, he went to the store, he bought food, and now he's all good. However, if you thought that was modifying store, you might interpret this incorrectly, and you might generate the next sentence as, because there is no food to be found, he went to the next store, right? Which is obviously not the case if you read this sentence carefully. And so you can tell what the correct interpretation is by looking at this tree. And you can look particularly at the distance between was and chef and was and store. And you will see that the distance between was and chef is only 1. They're directly neighbors. But was and store, you have to go through 4 different nodes here before you can connect them together. So basically, this is showing that it might be in the interest of a model like BERT to learn syntactic structure in order to help it perform its objective of filling in the mask token, or, for example, for GPT to predict the next token. So how do you probe for trees, right? That seems pretty complex. Like here we have this tree, but we have a BERT model, which is just predicting vectors of words. What does it mean? How can we get a tree out of this token level representation sequence that we have? So in this paper, Hewitt and Manning 2019, it's quite simple. So for every pair of words, you're going to identify, just train a classifier to predict the length of the path in the tree between those 2 words. So that tells you, like, for example, which words are neighbors, because they would be predicted with a length of 1, and which words are farther apart in the tree. And then you just need a way to figure out which words are lower down in the tree and which are higher up. And you can do that by putting using basically the norm of the representation and training a classifier if needed based on that. So you have 2 tasks that you need to do in order to recover this tree structure from BERT. First, predict the length of the path in the tree between 2 words. So I would have the representation of word 1, the representation of word 2. I would feed them to a classifier to predict the length. And secondly, predict the depth of a given word in the tree. And you can do this based on the just putting a classifier on top of the specific word representation, or you could just take the norm or some other metric of it to see if it correlates to the depth. So at a high level, it turns out that BERT does in fact encode syntactic structure, and you can reproduce these these parses just from these token level representations of the words in the sentence with these very simple probe tasks. So that's kind of impressive, and it does show that this kind of syntactic structure is useful for BERT when it's making these predictions. So that's about parsing. We also talked about numbers, right? Like, does it understand the meaning of numbers? We talked about this addition probe before, so I'll just skip over it. Another type of probe that we might want to look at is a more semantic probe, right? Does BERT understand various facts about the world? And so I might want to issue a query to BERT, like, where was Dante born, and have it output the correct answer to indicate that it knows this fact, or an incorrect answer which would indicate that it does not know this fact. So there was this data set created called Llama back in 2019, that essentially created a bunch of templated sentences like Dante was born in Mask. And you would feed this as input to your BERT model and look at the distribution of the mask token to see if this knowledge was encoded. And you could do this by manually defining some templates for different relations that you're interested in probing. So here's an example of some of the queries in the data set. So iPod Touch is produced by Mask, and then you can look at the distribution in the Mask token. The correct answer is Apple, so you see that Apple is also the highest probability completion, but there's also these other ones, like Nokia is only a slightly lower probability. Here you have sodium sulfide consists of Mask. The correct answer is, I guess this is a kind of strange, I mean, sodium is not all that. Anyway, so the model thinks that water is the most probable answer, so you might be able to conclude that this fact is not really well represented by the model. So again, all of these answers are just a single word because it's, of course, harder to probe for sequences. You need to actually decode from the model to figure out what is the highest probability sequence. The findings from the probe tasks conducted in this kind of knowledge-based, like Llama, suggest that BERT is also a knowledge base. So it encodes a lot of facts from its pre-training data set that are competitive with, and in some cases more comprehensive than knowledge bases that people have manually curated before. So it's a good way of picking up facts from a large piece of, a large collection of text. Okay, so I do really want to talk about this point, which I've alluded to before in this lecture, about probe complexity. So we've talked about a number of different probe tasks now, but how do we set up the probe? So there's arguments for both simple probes, which would be, you know, like a single linear layer or something like this, and complicated probes, which might be a big transformer or something like that. So for a simple probe, we might want to easily be able to access that information. So if we have a simple probe and it can capture, for example, coreference, that's a strong sign that the model has encoded coreference in such a way that even the simplest classifier could pick it up. However, if coreference is incorporated into these representations, but it's like maybe a nonlinear relationship between the representations and the coreference label, then maybe our classifier is just not powerful enough to pick that up. So there's arguments for both here. And this paper from John Hewitt at Stanford proposed this notion of control tasks. So in this case, if you're probing for a particular phenomenon, so let's say you're probing for part of speech, you want to know whether the final layer representation of cat, whether you can predict that this is a noun from that representation, whether you can predict that ran is a verb in the past tense, and so on. So one proposal is to create a synthetic task that's called a control task. So in part of speech, every word in your vocabulary is, every word in the input sentence is associated with a particular part of speech, right? So cat, here is a determiner, cat is a noun, and quickly is an adverb. So in your control task, he suggested we can randomly partition our vocabulary into different clusters. These are all completely random clusters. So you can see that the and ran belong to cluster 10. Quickly and dog belong to cluster 15. There's no relationship between these words. It's a completely arbitrary clustering. So here I can perform two tasks on sentence 1. The cat ran quickly. First, I can do part of speech tagging, which is trying to predict for every word some sort of label, the part of speech. I can also predict the control label. So which one of these random clusters does this word belong to? So the idea here is that the control task is completely arbitrary. This information that quickly and dog belong to cluster 15 is not something that you want the model to encode in the representations. It's also not something you want your probe task to be able to detect. If your probe task can detect that quickly and the probe classifier can detect that quickly and dog are in the same cluster, that's a sign that your probe network is probably too complex, because this is a random mapping that you do not want to be detected. So that is basically the point of the control task, is that it should be some sort of arbitrary behavior that does not correlate with the property that you actually want. And this paper showed that you can measure not only the accuracy of your probe network on part of speech tagging, which is this top curve here, but you can also measure the accuracy of your probe on the control task. So the idea is that as you increase the complexity of your probe network, so as you add more and more layers to the probe network, or more and more hidden units in this plot, so just making the size of the probe network bigger, you see that the performance of the control task also increases, to the point where if you have 1,000 units, 1,000 parameters in your probe network, the control task performance and the part of speech tagging performance are both almost above 90%. So this complex probe here is able to just learn this arbitrary mapping that you devised in your control task, which has no meaning at all. But just based on the data that it was provided, the model was able to learn these random clusters. But you can see that at, say, like a medium-sized probe network, the performance on part of speech tagging is still very high, but the performance on the control task is low. So this indicates that the part of speech information is easier to access than this arbitrary mapping that you've devised as your control task. And so the difference between the performance of the probe task and the performance of the control task is known as the selectivity of the probe network. So when you are choosing which probe network to use, you want to choose one where the selectivity of the network is high. So what that means that performance on the probe task is good, performance on the control task is bad. So this is how you might want to choose the complexity of the probe task. All right, so any questions? Yeah.
There seems to be an implicit assumption that when language models do their downscale tasks, they do it through the form of these simplistic probe tasks, right? That they will count the number of words, they have to account for what the word is. Is there sort of any analysis for the language models actually going through these steps of reasoning to what they're using?
Yeah, that's a great question. So all of these tasks that we've talked about in this lecture, they are very, very simple, and it is not necessarily the case that we understand how the language model uses these properties to do its predictions. And maybe in many cases it's not useful perhaps to know the part of speech of some word in the sentence. We don't have an idea of what operations the language model is doing over these representations at any given time step to predict the next word. So we just know in general that with these probe tasks, the information occurs somewhere in the representations, but we have no idea how it is used or accessed. That's still not something that we have a good understanding of. Yeah? So even if the network is really complex, why would it learn some random control task out of all the randomness that So remember that the control task you also provide training data for to the probe network. So it will learn specifically this mapping that is present in your data set that you're giving it. But the idea is that this is not a mapping that it should be able to learn. Yeah?
So this is almost trained by like adversarial example of what not to do?
So you are not interested in this control task at all. So in that way, it's kind of similar. But you're not adjusting your part of speech classifier based on the results of this control task. You're simply using it as kind of a baseline to assess whether or not the information is in the representation or the probe network is too complicated. So it's more of like an evaluation of the probe network itself. Is this chosen based on the validation accuracy of both the probe task and the control task? I assume you mean the selectivity. I'm not sure, but yeah, in both cases you would optimize the network based on the validation accuracy. Are there random linguistic tasks that the model might be able to predict correctly as well that are not linguistically correct? I'm not sure what kind of tasks those would be, but if you can devise some, you can easily try. So I'm not sure. All right, so I think we're out of time. So I had a couple slides at the end here about how you can use these probe networks to actually edit knowledge in the hidden state. So if you know, just really quick, if you know that John went to work at, you have this prefix and it predicts the store, but you want to add some knowledge in the representation of John to suggest that John plays the oboe, and you want to have it affect the language model's predictions such that instead of predicting the store, the model predicts the concert hall instead. There are now methods that allow you to actually patch the representations of particular tokens in order to add or remove knowledge about a particular entity to affect the generation. So one of these papers is in the readings for today. So if you're interested, you should check that out. And yeah, I will see you on Monday.